In this session, we are going to discuss about elementary signals and sequences and also singularity functions. So at the end of this session, the learning outcomes are you should be able to understand the concept of elementary signals and sequences. You should be able to explore the waveforms of singularity functions, and you should be able to analyze the relationship between the elementary signals and sequences. Now there are four elementary continuous time signals: continuous time unit step, continuous time unit impulse, continuous time unit ramp, and continuous time parabola. Now we are going to discuss about the continuous time unit step signal. It is denoted as u of t. It is defined by the formula u of t is 1 for all t greater than or equal to 0, that is positive time, and u of t is 0 for all negative time, that is t less than 0. The shape of the unit step signal is in the shape of a step. Now we are going to see what is a real world analogy of this unit step. Consider in a electronics lab, we have switched on a DC voltage source of 10 volts, let us say at t equal to 0 seconds. Then this constant voltage of 10 volts, which was generated at t equal to 0 seconds when the switch was pressed, can be represented as V of t is equal to 10 u of t. Now we are going to discuss about the unit impulse signal. What is the unit impulse signal? It is also called delta function or Dirac function. It is denoted by delta of t. It is defined as delta of t is equal to 0 at t not equal to 0, and at t equal to 0 its value is very large, and the area under the unit impulse signal is that integral minus infinity to infinity delta of t dt is 1. We can see the graphical representation of delta of t, which is of course the impulse signal. So all the values at negative time and all the values at positive time, they are all 0. Only at t equal to 0 at the origin, delta of t is having a large value. What is a real world analogy for the impulse signal? In certain practical situations during some power outages, we will observe that when the power comes back, there will be a sudden large voltage spike that is lasting for a very short duration, like a very high voltage. And these are called transient signals, and impulse signal is used to model these type of transient signals. Now we are going to discuss what is the relationship between impulse signal and unit step. We already have seen the integral of delta of t dt from minus infinity to infinity is 1, and we can rewrite the same equation as integral minus infinity to t delta of tau d tau is equal to 1, which is nothing but the unit step signal. Therefore, by integrating the impulse signal, we are going to get the step signal. Now conversely, by taking the derivative of the unit step signal, we can obtain impulse signal as shown by this equation. Now we are going to discuss about unit ramp signal. The unit ramp is denoted by R of t, and it is defined as R of t is equal to t for positive time and R of t is equal to 0 for the negative time. Now this is the shape of the unit ramp signal. Now we are going to see what is the relation between the unit ramp and the unit step. So we can do the integration of the unit step signal, the integral of minus infinity to t u of tau d tau, which will be equal to t, which is the ramp signal. Therefore we can write the equation as integral minus infinity to t u of tau dt is equal to r of t. Thus, by integrating the unit step, we can obtain the unit ramp. Conversely, by taking the derivative of the ramp signal, we can obtain the unit step as given by this equation. Now we are going to discuss continuous parabola signal. It is denoted by P of t. It is defined by the following equation: P of t is equal to t square by 2 for all positive time values, which is shown here on the positive time side, and for all negative time it is 0. Now we are going to see what is the relationship between unit parabola signal and unit ramp signal. Now we will integrate the ramp signal. The integral of minus infinity r of tau d tau will be is equal to t square by 2, which is nothing but the parabola. Hence the integral of the ramp signal r of t is the parabola signal. Conversely, by differentiating the parabola signal, we can obtain the ramp. So d by dt of p of t is r of t. Now we are going to discuss about the singularity functions. Singularity functions are discontinuous functions and their derivatives are also discontinuous. So a singularity is a point at which the function does not possesses a derivative. So if the function is discontinuous, then it can be called to have singularity at the point of discontinuity. Now, if you see all the four elementary continuous time signals, unit step signal, impulse signal, ramp, and parabola, they are all singularity functions. They have a singularity at the origin t equal to 0. Now, we are going to see what are the properties of the singularity functions. Scaling. We can scale these singularity functions both in amplitude and time. Shifting. The singularity functions can be shifted either in the forward direction of time or backward direction of time. And there are certain useful relationships by integration and differentiation. Now here we are again just giving a summary of the singularity functions. Differentiation, the derivative of the unit step is impulse function and the derivative of the ramp is the step function. Similarly, now we will see the integration. The integral of the impulse is unit step and the integral of unit step is the ramp. Combinations. We can combine these singularity functions to generate more complex waveforms. Here we are seeing what are the applications of the singularity functions. They are applied in circuit analysis, they are applied in control systems, signal processing and mathematical modeling. Now we are going to discuss about elementary discrete time sequences. There are four elementary discrete time sequences: unit step sequence, unit impulse sequence, ramp sequence and parabola sequence. Now this is the unit step sequence. It is denoted by U of n. It is defined by this equation. For all positive time values of n, U of n is always 1. That is this side of the waveform. Now for all negative time, U of n is 0, which is the negative side. It's always 0. We are going to discuss now unit impulse sequence, which is denoted by delta of n. It is having only single value at n equal to 0, where the value is 1, and for all n is not equal to 0, delta of n is 0 on both negative time and also positive time. It has only a single value of 1 at n equal to 0, which is the origin of the time axis. Now we are going to see what is the relationship between the impulse sequence and step sequence. We can write that the running sum of the impulse sequence will be the step sequence as given by this formula. We can also state that if we take the first difference equation of the unit step, which is u of n minus of u of n minus 1, we will get unit impulse sequence. Next, we are going to discuss the unit ramp sequence. It is denoted by r of n. R of n is simply n for all positive time and it is 0 for negative time. Now, what is the relationship between the ramp and the step sequence? We can write R of n is equal to n into u of n. Next, we are going to discuss about parabola sequence. This is denoted by the symbol P of n. The values of the parabola sequence are n square by 2 for all positive time, which is shown here in the parabola shape, and the parabola signal is 0 for all negative time, as shown on the negative time side. Now, what is the relationship between parabola sequence and step sequence? The parabola sequence P of n can be denoted as n square by 2 into u of n, where u of n is the step sequence. I want to thank all the students for your patient hearing. Thank you.